Great. Okay, so hopefully this will be a valuable wee lecture to discuss some of the fundamental aspects of chemistry that we need to know about when using UKCA. So, thanks, Luke. Yeah. So this is a very, very brief introduction, so I'll try and be gentle. But to begin with, what I wanted to sort of also talk about was what we mean by modelling, and then how we can kind of use conceptual ideas about what a model is to then go on to think about how we can think about modelling chemistry in the atmosphere. So lots of ideas and definitions about what a model is. To some people, a model might be y equals mx plus c. It's a very simple model. And to other people, a model might be a very complicated Excel spreadsheet. And then to others, a model might be something like UKCA, which, as Luke said, very scarily, was 140,000 lines of Fortran, 238 files, and which maybe, other than Luke, nobody else in the world knows in detail. But the key thing is that modelling is a theme in science that's been going on for a very long time, and modelling complex systems as well has been going on for a very long time. As an example of a complex system, weather is probably one of the most well-known complex systems, and numerical prediction for weather has been going on for over 150 years. So this is an extract from the Times newspaper with one of the original weather forecasts produced in 1861. But essentially, when we think about what a model is, one idea is to just start on paper and to write out what we think the question is that we're trying to solve first. So we define what our question is, and then we think about developing a simple, and one way to do this is as simple as possible, mathematical representation of the processes that we think are involved in the question that we're trying to solve. So then once we've got the mathematical representation, and we know what we're trying to do, we run the model, and we determine some metrics which allow us to diagnose and evaluate our model against some real data. So those could be observations or any other sort of quantities that we think represent reality. And then we go through this kind of loop of iteratively improving our model. Our model will include lots of parameters, no doubt, and so some of those parameters might be uncertain, and so what we'll do is we'll modify those parameters to try and get some agreement with these real observations. And then once we've kind of closed this loop and we feel like we've got a model which reproduces well reality, then we can use that model to make predictions about, for example, the future state of the atmosphere. And so when it comes to modeling atmospheric chemistry, pictorially, so again, so a wide range of people with experience in chemistry, these squiggly lines, do they mean things to everybody? So basically the vertices are carbon atoms, and the lines are representing carbon-carbon bonds. So we're not really showing all the hydrogens, but this is butane up here. And then what this diagram is showing is the mechanism of oxidation of butane in the atmosphere. So butane contains just carbons and hydrogens, but in the atmosphere where we have lots of oxygen, the ultimate fate of carbon is to form carbon dioxide. That's the kind of the lowest energy state of carbon. This is a higher energy state of carbon. And so what happens to go from butane to CO2 is all this lovely magic, all this lovely chemistry. And each arrow here represents a different chemical reaction. And atmospheric chemists like to, well, particularly James likes to, make these cartoon diagrams to show all of these beautiful processes converting our butane molecule all the way through to these intermediates, which we're kind of denoting here in these square boxes, to the final products here of this oxidation process. But you know, this doesn't look like maths, this doesn't look like something we can put into a computer. So what we have to do is convert this beautiful picture into a series of mathematical equations. And so just to kind of focus at the beginning, so in this case here, butane isn't something that's generated in the atmosphere, it's produced by emissions and emitted into the atmosphere. So we need to think about what this emitted species reacts with in the atmosphere. And the prime thing to think about really is reactions with the hydroxyl radical, which is like the atmosphere's detergent. So the hydroxyl radical really is unhappy. You could think about it like that. And it really wants a hydrogen atom to turn it into water. So as long as there are some things with hydrogen atoms around, the hydroxyl radical is going to try and steal those. And when it does that, it's going to kickstart this whole chain of chemical reactions. So we've got hydroxyl reacting with butane. And one way to represent that is by thinking symbolically an equation like this. So A could be the hydroxyl radical, and B could be butane, and they go on to form some products, which we're just calling C and D. And so what we're interested then, in terms of solving this problem, is understanding how the concentrations of these species evolve with respect to time. And so to do that, we have to kind of use calculus, and we have to think about writing a differential equation which represents the change in concentration of species with time. So if this reaction here has some coefficient which tells us how efficient the reaction is, we could give that coefficient a letter K. What we term those Ks as is rate constants, because they're kind of constants for this reaction. By multiplying K by the concentrations of A and B, we get something which has a dimension of changing concentration with time. And throughout your kind of experience with UKCA and your experience with atmospheric chemistry, you'll probably get used to a new unit of concentration, which is the units that we use, which is molecules per cubic centimetre. So most of the time with chemistry, you probably use moles, or moles per decimetre cubed, or something like that. Atmospheric chemists, I don't know why, but they don't like that. They like molecules per cubic centimetre. And it's not because it kind of comes out as a nice number. What's a typical concentration of ozone? 10 to the 12 molecules per cubic centimetre. It's not a very nice number. It's not like 1. Concentration of air at sort of surface temperature and pressure, 2.5 times 10 to the 19, also not a nice number. But for whatever reason, we're using molecules per cubic centimetre for concentration, and we're using seconds as our base for time. So in this case here, we've got a rate of loss of A with respect to time, which is denoted by this. So minus, because we're losing A in this reaction, times K, the rate constant for this reaction, times the concentrations of these two species. And so we can think about this thing in red as the rate equation, and the thing here, dA by dt, is a continuity equation for our species. So dA by dt is equal to minus dC by dt, because A is a reactant and C is a product. And so the rates of change here are just equal and opposite. But we can also denote things like the loss rate. And so we could use the letter L to denote the loss rate, and we're denoting this as loss of A. So that's just the same thing here. Similarly, we could define a production rate, and again give it the symbol P, and a subscript for what we're talking about. So the production rate of molecule C is now just given as exactly the same as the loss rate of A, but just changing the sign. Hopefully that's cool. So coming on to these rate constants, and this is where I realized that if you don't do a lot of chemistry, now you'll get confused, because I've got 2 A's. So when it comes to these rate constants, they're not really constant. So K is a rate constant. Can you see this? No? Or otherwise known as a rate coefficient. Usually, we can think about it as a function of temperature, but sometimes also it's a function of pressure as well. So M here is equivalent to pressure. And in this case, where we have this example here for what a rate constant looks like, A we call the pre-exponential factor, and just to note that it's not the same as the A here. Apologies for the use of A's. But what we see is that A gets multiplied by this thing here in this bracket, which is giving us on the numerator a term which we call the activation energy, and on the denominator a constant, the gas constant, times the temperature. So as you know, for something within an exponential, we need it to be dimensionless. So if the numerator is an energy, then the denominator must also be an energy. So RT is just the thermal energy of our gases. So we know that temperature is a measure of the kinetic energy of our gases, so R times T is just giving us that kinetic energy that the gases have. So the higher the energy, the smaller this fraction, and then the closer we are to realizing this A factor. In other words, what this A factor is the rate constant at infinitely high temperature when we've got infinitely high kinetic energy. And these activation energies and A factors have all been calculated for us. Do we have any experimentalists in the room? No? Everyone's a modeler, like people. I mean, for those of you that like doing experiments, my understanding is measuring things like rate constants are particularly tedious and laborious. And thankfully, people have been doing this for about 60 years. So we now have tables of A factors and activation energies and rate constants, so we don't need to do anything more there. But we do need to appreciate them, and when it comes to adding in reactions into UKCA, you're going to have to think about the sources of information to get things like the A factor and the EA factor. And to be honest, UKCA also uses different forms of this same type of equation with some slightly different tweaks, but that's something you'll get onto when you start to actually code up new reactions, so we won't dwell on it too much now. But what we will dwell on is the fact that we can kind of think about reactions of different orders. And so before we've been thinking about two things coming together. So the rate of that reaction depends on the concentrations of both things. But if we have a situation where the concentration of one of those things is really large compared to the other, then effectively the thing which is really large in concentration doesn't change with respect to time. So dB, in this case, if B is really large compared to A, dB by dt would be about 0. So what that means is we can make an approximation which reduces the dimensionality of this problem of A plus B going to C plus D into something which looks more like A kind of just goes to C plus D. And we've introduced a new rate constant here, K prime, where K prime is actually just equal to K, our original expression, times the concentration of B. And what we've done is we've gone from something which was what we would have called a second order rate constant, second order because it depended on two concentrations, to what we call a first order or a pseudo first order rate constant. And now again, if we think about this continuity equation, so we've got change in concentration with respect to time. So now that kind of means that the dimensions of K prime must be inverse time. And that's quite nice because now it gives us access to something which we can use to characterize the reaction, which we call the time constant. And the time constant is just the time it takes for our species concentration to drop by 1 over E. And so here for that dA by dt, that very simple system, what we call first order decay, we can see how if we change the magnitude of the rate constant, the time constant, which is just 1 over that, also changes. So when the rate constant was equal to 1 per second, the time constant is just 1 second. And you can see that on that graph here. The time it takes to get to 1 over E, so we've got about 37% of the concentration of A left, is 1 second. Similarly, when we go to K is equal to 2 per second, tau, the lifetime is half a second, which we can also see from this graph. So time constants are just a really useful way of thinking about the speed of reactions in the atmosphere. And what we're always going to be having to consider is how fast chemical processes are happening relative to other physical processes in the atmosphere. So those key things are like turbulent mixing, which is fast, large-scale dynamical mixing, say like the Brewer-Dobson circulation, which is very slow, and we'll have to think about these relative processes. So that's kind of, given us this idea of first-order kinetics. And one of the most important reactions which happens in the atmosphere, which obey this kind of first-order kinetics, is photolysis. And so confusingly, rather than using K's, we're moving to J's. So the letter J now represents that first-order coefficient which we use to represent the rate coefficient for photolysis-type reactions. And these photolysis-type reactions we can basically compute by knowing what the absorption cross-sections are of our molecules. So at some point, maybe at school or otherwise, you might have done an experiment where you have a solution with some molecules and you pass some light through. Remember doing this type of experiment? Yeah? And then you measure the light coming through your little cuvette. And what you see is that some of the light has disappeared. So the molecules in this cuvette have absorbed some of the photons which are present in this light. And you can measure the intensity of light. So this would be I0, and this would be I. And the ratio of that intensity of light is going to be determined by how many molecules we've got, the path length of the light, L, and some coefficient. And that coefficient, which if we kind of think about these experiments that you would have done, would have been called an absorption coefficient or an absorptivity coefficient or something like that. And this relationship is basically the Beer-Lambert relationship, the Beer-Lambert law. Now, in atmospheric chemistry, we're not dealing with aqueous solutions of molecules, so rather these are gases, and these are specific gases which are absorbing at a specific set of wavelengths of light. And we use the symbol sigma to denote the cross-section that these molecules have. And so if I think about something like an ozone molecule, well, what does the cross-section mean? So what it doesn't mean, it doesn't mean the geometric area of our ozone molecule. Because that geometric area is sort of roughly, it's like a triangle, right? So we could roughly work it out if we know the size of the bond lengths of our ozone molecule. We could say this is roughly how big an ozone molecule is. But the cross-section actually depends on wavelength. So we know that it's not a constant. And so it's actually related to the electronic structure of our ozone molecule. And so if we think about what happens when an ozone molecule or any molecule absorbs some light, that light goes into the molecule, that light is an energy, and so it makes the molecule either spin around, rotate, or vibrate. And if we think about going to higher and higher energies, then effectively what we can do is we can promote the electrons, which are, you might have drawn dot-cross diagrams or something like that. But we can promote those electrons into what we call higher energy orbitals and break the molecule apart. And so using the Beer-Lambert law, again, we don't have to do this, thankfully. These are even worse lab experiments than rate constants, cross-sections. They're just like hideous. But yeah, using textbooks, we can kind of determine how these cross-sections vary as a function of wavelength for the different molecules that we're interested in. And then we just multiply those by the other terms in this equation. So the other term in this equation that we need to think about is phi, which is also a function of wavelength, and that's the quantum yield. And the way that I think about that is that basically what we're talking about is a process where, say, Yeah, let's say ozone. So O3 plus a photon goes to O plus O2. And we're breaking one of these bonds in the ozone molecule. So if I'm an ozone molecule, I can absorb photons at lots of different wavelengths. A lot of them will just like spin me around, or they'll make me vibrate. But only some of them will actually be high energy enough to make one of the O atoms pop off. And that's what the quantum yield is measuring. So for every photon that I absorb, how many of them lead to a dissociation? So it basically goes from 1 and 0, and if it's 1, it means that the wavelength of photon that I'm interested in is high enough energy for me to break apart. And if we think about what a graph of the quantum yield looks like as a function of wavelength, then it basically looks like a square function. There are important details which mean it's not quite square, and it kind of has a exponential tail, but we won't worry too much about that. So then the last bit of this equation is kind of the all-important flux of photons. So we're just calling that F. And the flux of photons, as we probably all know, depends on the wavelength of light that we're interested in. So the sun is kicking out loads of photons in the visible part of the spectrum, fewer photons in the X-ray, more photons in the UV, not many photons in the IR. The Earth is kicking out lots of photons in the IR, but no photons in the UV, and definitely no photons in the X-ray part of the spectrum. So this kind of depends on our source of radiation. But for atmospheric chemistry, the source of radiation is the sun. And what we need to think about is how the flux of photons changes as we traverse through the atmosphere. And so if we think about what a graph of that might look like, altitude versus wavelength, altitude versus flux. So at some wavelengths, the flux will be basically the same through all altitudes in the atmosphere. What that's saying is that the molecules which are present in the atmosphere aren't really absorbing those wavelengths. So what wavelengths will they be? Visible wavelengths, because if you go up in a hot air balloon, you can see just as well as you can at the ground. So there's not a lot of absorption at those wavelengths. But if we go to the UV, then we start to get this exponential drop. So that would be UV, that would be vis. For the UV, we get this exponential decay of the flux of photons with decreasing altitude. So remembering that like all the gases are pulled down by the force of gravity towards Earth's surface, so we have more and more gases at the surface. So we've got more and more things absorbing the photons, so we have that exponential decay. Okay, so photolysis, we've done thermal reactions, and then let's just put it all together. And so this is really what UKCA box model is doing, is solving this continuity equation for us. And we can kind of split it into a number of terms. So I talked about production and loss, Px and Lx, and we also have emissions as another source of our molecules. As I said, for butane, there's no chemical production of butane in the atmosphere. There is on Titan and some other exoplanets as well produce butane. But Earth's atmosphere doesn't produce butane. Instead, things like the petrochemical industry probably produces lots of butane. We then also have another loss process which we refer to as deposition, and that's just really molecules sticking to the surface of the Earth or to vegetation. And then we have this sort of transport. If we think about discretizing this equation onto a grid and solving in a box or something like that, then we might have a flow through to transport of our species out of that box. So that might be also a loss. The difficulty really lies in parameterizing all these individual bits. So emissions, they are just what they are. Sounds a bit stupid, now I said that. I think the key thing is garbage in, garbage out. So most of the chemistry results from emissions of precursors. So if you put in, shit, emissions data, then there's no way, given all that complexity of the chemical reactions, that you're going to actually simulate anything that looks good. If it does look good, you've got to ask yourself, why? WTF? So again, the good thing is lots of people spend their whole careers working on emissions inventories, and there are some great ones out there. You just need to Google for them, or speak to some of your colleagues, or speak to Luke, or anyone at the UKCA course can kind of tell you about trusted places to get emissions. Deposition. Again, deposition is kind of modeled as a series of processes in UKCA. And so in UKCA, we basically have three processes which get added together like resistors in series. And that involves an aerodynamic resistance term, a cuticular resistance term, a stomatal resistance term. Again, there's kind of lots of details there. And again, what we need to do is just be aware that if we're adding in a new species into the model, we need to think about whether deposition is an appropriate loss process for it. And the way we can do that, again, is by looking at references to define some of these parameters. And then the production and loss. So we've kind of given some of these pictures of what chemistry looks like, and we need to kind of build up a picture of what happens to our molecules in the atmosphere. Once we go from that conceptual picture, we can start to go and find the information. And again, a lot of this is all tabulated. So the IUPAC, which is the International Union of Pure and Applied Chemistry, something like that. They have evaluated kinetic data, so lots of wise, predominantly old white men, sadly, sit together and they talk about, when I was a lad, I measured this rate constant to be 1.25 times 10 to the minus 15, and scratch their bellies and say, yeah, I think you were right, Similarly, the National Institutes for Science and Technology in the US, they have another database that you can actually just search to find out rate constants for reactions. Their database doesn't have any evaluation, so they don't have old white men going around saying, yeah, I liked yours. Yeah, yours was really good. I think yours was good. But it does provide a great way of finding some kinetic data. So once you've found that kinetic data, you then want to kind of piece together your reaction mechanism, and again, thinking about rewriting your reaction mechanism rather than as squiggly lines, as reactions of the form A plus B goes to et cetera, et cetera. And so for methane, we could think about a really simple methane mechanism looking something like this. So methane reacts with the hydroxyl radical to give us a product, carbon monoxide, and carbon monoxide can also react with the hydroxyl radical. And the hydroxyl radical can also react with other things, and we're just denoting those other things by X in this case. So the rates for these reactions are then given by the rate constant, for this one. So this is K5 times the concentrations, as we've seen before. And here are the values for the rate constants. So then we can just write down our continuity equations. And here S is referring to a source, so it's exactly the same as I was writing E. So emissions of methane, emissions of CO, and some source of OH. There aren't actually emissions of OH, it's a photochemical source, and that's why we're kind of using S here. So this is what UKCA is doing for you. All that you have to do is write into the UKCA Fortran equations like this, where you impute the value of the rate constant and the reactants and the products. ASAD, which is the chemical solver in UKCA, will then write symbolically these equations, which is really nice because it's really easy when you have lots of reactions of A to miss one out. So instead, the Fortran code symbolically determines what these continuity equations should look like, and then it works out the basically like you can think about it, the sensitivity. So the rate of change of methane with respect to time with respect to methane. So this matrix here is basically telling us how each species changes with respect to each species. And what we have is that this matrix needs to be solved using some linear algebra. So we won't bother, doing linear algebra now, but just know that, this is where a lot of the computational time comes in UKCA. So a lot of the time is spent moving the molecules around in the model atmosphere, and then a lot of the time is spent solving this matrix. And that's really simple. So that's 3 reactions to represent methane in the atmosphere. But actually, if we think about methane, how would a chemist write down the oxidation of methane? I'd actually come up with a lot more reactions. So something probably more like this. And implicitly, what we've done previously is basically remove any of the fast reactions and the very short-lived species. And this is one of the key steps in what we would call mechanism, I've forgotten the word for it. Yeah, mechanism reduction. Thanks, James. So a lot of mechanisms that we're using in things like Earth system models or CTMs have gone through this mechanism reduction step. There's a lot of work at the moment to try and automate this and to try and generate sets of rules so that you can apply an algorithm to do it. But also historically, it's been people like me, people like James, have actually just kind of used intuition and some rules that we kind of have developed ourselves to do this process. But by basically kind of going through that mechanism reduction process, then we emit things like this CH3 radical, and so we skip this reaction here. And one of the arguments for skipping that reaction is if we look at the time constant for that reaction, well, it's 1 millisecond. The chemical time step in UKCA is 1 hour. So what's the point in trying to solve something that's happening on the order of milliseconds when we've only got an hour that we're solving chemistry over? And same again for all those. But like I said, let Assad do the hard work for you. There's a really nice paper in GMD where Emre, one of the postdocs in the group a couple of years ago, kind of did a slight tweak to how we solve the equations in Assad and generated, was it like a 7%?
2.5% over the global model, but
yeah.
in UKCA that was...
Yeah. One line code change and significant impact on model runtime. Okay, so then, and kind of just to, again, put my visualization of how the UKCA box model works. Effectively, we've got these inputs at the surface, things like emissions. And if we look at the emissions inventory data, they'll often give us it in terms of things like molecules per area per time. So if we divide that by the height of the box or the volume, the height that we're kind of pseudo-simulating, then we get something which is in molecules per cubic centimeter per time. So that's kind of similar to what we want in terms of chemical production and chemical loss. And then we have deposition, which again we can think about as a first order process. And if we want to have some flux out, then we need to kind of code that in. The box model isn't really set up to have fluxes of molecules in it. It's really set up to do the chemical production and loss, deposition and emissions. And so inside chemical production and loss, that's, as Luke was saying, like where photolysis would be. And then, like, what does it look like when it's the full UKCA? Well, you can just think about it as millions of boxes stacked together, and now the boxes are talking to each other. So now we have transport between them. So that becomes quite important. And as we've kind of gone through time, the size of the boxes that they're representing, compared to the Earth, are getting smaller and smaller and smaller. And as we move to things like ELFRIC in the future, and for those of you that are kind of going to use other models as part of your work, you might also start to see that the idea of a regular sort of grid of squares or rectangles gets thrown away, and instead we have things like cube spheres or icosahedral grids, which are now becoming kind of more and more fashionable because they have much nicer properties, like not having a singularity at the pole, which is quite important. And then, am I good for time?
Yeah.
I've got 15 minutes. Okay, I've got one slide.
Okay. Got 20 time for questions.
Okay. So my last slide comes from a great, I guess, mentor in some ways, Dick Derwent, who showed this at a seminar he gave here many years ago. And Dick was kind of really instrumental in terms of providing leadership in modelling atmospheric chemistry in the UK. He spent most of his career at the Met Office, but he actually did a PhD here and his undergrad here in Cambridge. And for his sins, he did a lot of the kinetic laboratory measurements, but then saw the light side and moved over to modelling. And Dick used this as a way to just kind of make us think about what are we doing here, people, when we're comparing models and reality. And this was kind of, motivated by this lovely, I think, is it Tracy Emin piece of art, which was a Turner-nominated artwork and sold for £150,000 on the right, and on the left is a Lego model of it. And you could, arguably say the Lego model is good. If you knew your art and you were just presented with the Lego model, you would say, oh yeah, Tracy Turner, whoever it is, I've forgotten her name, sorry, Tracy Emin. Yeah, that's what that is. Whereas clearly, it's not quite reality, right? And I think for me, I always come back to this image to ground myself in not running away with the idea that even though the model can generate things which look like reality, the model isn't reality. It's a tool. It's a tool which we use to answer specific questions. And again, we need to kind of think about what are the metrics that we use to determine whether or not our tool is fit for purpose. Are you giving people these slides? I'm quite happy. Yeah. So, what I don't have time for in 15 minutes is to go through all this model evaluation stuff. But have a look at it if you're interested, because I think model evaluation is really important. And I think probably the greatest amount of time you'll spend with using models like UKCA will actually be in the model evaluation process, not the finding rate constant data and putting it in. And yeah, happy to take questions. Yeah.
Thanks, Alex. That was a great talk. So, any questions? Joe? We can go quite far back.
Yeah.
When you first, when you said that there's different aims, can you clarify what there's an aim to that, right?
Yeah.
And then some relationship between that and the
There is absolutely zero relationship. My bad, as we say. So, K equals A times blah, blah, blah. That A is just what we call a pre-exponential factor. So, A... Yeah, so A in square brackets is a species, a molecule. A in relation here is just, I should have called it, I really apologize, because it's just chemistry, isn't it? You just get so used to it. Should have said K equals alpha times exp of minus EA over RT. Yeah, so the EA, yeah, exactly. So if we've got A plus B goes to C plus D, that sort of difference there, that hump in, so we've got energy on the y-axis, that hump there is what we call the activation energy for this reaction. And the more kinetic energy you have, like the more energy you have to go over that hump. Does that make sense? So like at 0 Kelvin, like hypothetically, you've got basically very, very cold molecules, and they won't react. And then as you heat them up, they start to collide around, and some of those collisions have got enough energy that they can overcome that barrier. And the fraction of molecules that have sufficient energy is just given by that exponential.
So EA is for this reaction.
Yeah.
And then without like a constant, or is that also
It's a constant related to the reaction. So if you take this to its limit of like infinite temperature, the exponential, then you basically just get 1. So you've just got alpha, k equals alpha. And the way that experimentally that's determined is if you plot 1 over t versus k, you'll make measurements, say here, and you extrapolate, or ln k, sorry. You'll extrapolate all the way up to the intercept, and you'll say, oh, that's my high temperature limit for the reaction. Woohoo? Yeah?
So normally for the beta constant, there's uncertainty.
Yeah.
For the UKCA, if you do the model evolution,
Yeah.
so normally anybody do the range of the constant.
So we don't have the way to. So yeah, can I draw this? So basically, you could think about a vector of rate constants for all, like where each k is for each of the reactions. And in UKCA, we just have one set of values for each rate constant. But actually, K1 has some uncertainty with it. And some of the uncertainties are actually quantified and tabulated. So you can find in the literature a value, beta, which says that K1 has an uncertainty of plus or minus 20% or 40%. In some models, what you're able to do is kind of convolve the mean estimate of the rate constant with its uncertainty and look at how that propagates onto your results. And so quite commonly, this is done in box modeling, actually. So where you have time and the concentration of your species that you're trying to model, you might have that this is coming from the mean rate constant. So you're happy with a bar to represent a mean. And then if you use like a technique like Monte Carlo sampling, where basically you kind of randomly sample the uncertainty vector, then you might end up with an envelope, right, of possible values for the concentration of X. So I think this is what you're getting to, Woohoo. So we don't do that in UKCA because you have to kind of go through many iterations. So to generate something like this with a box model for like a scheme of 100 reactions might involve on order of 1,000 simulations. So if we were to do 1,000 UKCA simulations,
it would be employed for a long time.
Yeah, we wouldn't do anything else. So currently, we just don't have the computational ability to do that routinely. There are really nice approaches. So in my sort of evaluation slides, I talk a bit about perturbed parameter ensembles and model emulation, where you might generate a smaller subset of experiments to probe some of the uncertainty that comes from chemistry. Oliver Wilde, who some of you might know, he's been like leading some of this on the chemistry side, and there's some really great papers that Oliver's publishing and has published on that topic. But to answer your question, no, we can't do that in UKCA at the moment.
But as you principle, develop some technique so they can just set run the model once, actually we can verify the range.
Yeah. So, well, so Ken's group have kind of pioneered the use of perturbed parameter ensembles to generate emulators. Yeah, and so for those of you that don't know, like an emulator is a statistical surrogate model based on your simulator. So UKCA is a simulator, it simulates chemistry. And if you do enough UKCA simulations where you perturb parameters in your model, you can fit some functions to your output data to generate a statistical model, a surrogate model, an emulator. So those, that's not really, no. It's like there's a bit about it in one of Oliver's papers where they compare UKCA, Oliver's model, FSGC, whatever it is, UCI, and the NASA GIST model. And they basically look at what are the important parameters for determining the oxidizing capacity and see that in different models, different parameters come out. But they don't then emulate the output, so they didn't generate an emulator. So they just did the perturbed parameter ensemble.
Yeah. Do you always have to, is the smallest time circle in UKCA 1 hour?
Yeah, it's so in ASAD, so I don't know how many of the files of 238 are ASAD related.
Not the. I can't remember off the top of my head.
Yeah, but basically, like there are bits in ASAD where you can sort of modify things like that.
So you can change the time step, and in fact, you can do that. And I think you might even do that as part of the tutorial. Generally, in the global model, it's fixed at 1 hour, and that's because a lot of work has been done to assess what's the best in terms of computational performance for we want to run for 100 years, and we don't want it to take 100 years to do that run, compared to what's best in terms of the chemical results that come out.
Yeah.
And it's always a bit of a balancing act, because you get the balance of people saying we want to run even faster, can we have it longer, and then have chemistry folks go, actually, no, we could really do 20-minute time step or 5-minute time step, and then it's a little bit of tension there.
Yeah, I wouldn't touch it personally.
I mean, people have played around with it, and sometimes it looks a bit different, but you can't necessarily say it's meaningfully different. It just the answers will be different because the time step is different. But statistically, I'm not sure whether you have to get a different result, which is the main point that we want to get.
Yeah.
If it gave us a different result statistically, then we have to investigate it further. But they're not.
It's along the same lines, because it's something I struggle with a little bit, because I work computational breakdown and volume models.
Yeah.
So the atmosphere global model is working on finite difference. It then stops, and then you do the chemistry step. Now the atmosphere is going over 15 minutes or 20 minutes time step there. How do you consolidate those? So is the chemistry at the very beginning or
Well,
the global time step, or is it at the end?
like when is it valid?
Yeah, but when, yeah.
Well, I think though that kind of comes down to again the question about the timescales of the two different components of the system. So the timescale of the transport is much quicker than the chemical evolution timescale. So actually, the chemical evolution timescale is is valid over that whole hour. The way that things have been picked through the mechanism development cycle, I guess, means that they're not the super fast reacting species, or if they are, they're in steady state, like OH is going to be the same in 5 minutes and 10 minutes and 20 minutes. And so I would say it's not like the weather forecast personally, where the weather forecast at 10 a.m. is valid for 9 o'clock to 10 o'clock, not at 10 o'clock.
Yeah, I mean, it gets a bit. I mean, because the way it's done computationally is it's done right to the end. So you can think like it's done right to the end, but actually, like these processes are going on throughout the time step. It's being moved around, and the chemistry is going. It doesn't just stop. Saying, all right, we're still now. Let's do some chemistry, and then let's carry on. and it's computationally, you have to make a choice as to how you break it up. I guess you could, I don't know if there's ways, you could think about doing them in, but yeah, it's done in that particular way, it's done at the end. In fact, within chemistry, the time step can be halved if it's hard to solve, and it has a little half of the time step to allow it to do it. Then it has to do it twice. It's done half an hour time step, not an hour time step. It's even harder, it's 15 minutes time step, it has to do it 4 times. So it's all a kind of computational construct to get to reality in terms of the Lego bed at the end.
Yeah, and I guess that is the thing, right? That it's not real. It's just a way of breaking down the problem into some mathematical equations which you can solve.
The missions are done every 20 minutes. They're around time step. They're done sort of mixing stuff. But the chemistry is only done every hour because computation can't do it. So what's going on with those missions that are done every 20 minutes? So it's even time steps are on chemistry. But they move around, but they don't actually get chemistry happens to until the hour. So, good question.
Yeah.
Especially
yeah.
No, well, thanks, Alex.
Thank you.